The unseen force. An introduction to radiation. Radiation. The word itself carries an air of mystery, even fear. It conjures images of danger zones, hazardous materials, and invisible threats. It speaks of invisible forces, of potential danger lurking unseen. The very idea of something that can affect us without our knowledge is unsettling. And yet, radiation is all around us. It's not just confined to the realms of science fiction or disaster movies. It's a natural part of our world, emanating from the earth, the cosmos, even our own bodies. Every day, we are bathed in a sea of radiation, most of which is harmless. In its simplest terms, radiation is energy traveling through space. This energy can be in the form of waves or particles. This energy can take many forms, from the warmth of the sun to the radio waves carrying our favorite songs. We rely on these forms of radiation for communication, warmth, and even life itself. But it's the invisible forms of radiation, the ones we can't see, smell, or feel, that often spark the most curiosity and concern. These are the types of radiation that can have profound effects on our health and environment. These invisible rays, known as ionizing radiation, possess enough energy to knock electrons off atoms, altering their very structure. This can lead to significant changes at the molecular level. This process, called ionization, can damage living cells and even cause mutations in DNA. Such mutations can lead to various health issues, including cancer. It's this potential for harm that makes understanding radiation, its types, and its effects so crucial. Education and awareness are key to navigating the complexities of radiation. While the dangers of radiation are real, it's important to remember that it also plays a vital role in our lives. From diagnosing illnesses to generating electricity, radiation has many beneficial applications. From medical breakthroughs to clean energy production, radiation has the power to both heal and harm. X-rays and CT scans allow doctors to see inside the body, while nuclear power provides a significant portion of the world's energy. By understanding this duality, we can harness its benefits while mitigating its risks. Through careful management and continued research, we can ensure that radiation remains a force for good in our world. Delving deeper, the science behind radiation. At its core, radiation is a release of energy from unstable atoms. This energy can take various forms, including particles and electromagnetic waves, and it plays a crucial role in numerous natural and technological processes. Atoms, the building blocks of all matter, consist of a nucleus orbited by electrons. The nucleus, which is the atom's core, contains protons and neutrons, while electrons move around this central core in defined orbits or electron shells. The nucleus contains protons and neutrons, and it's the balance of these particles that determines an atom's stability. When this balance is disrupted, the atom becomes unstable, leading to the potential release of energy. Some atoms naturally exist in an unstable state, possessing excess energy within their nuclei. This instability can be due to an imbalance in the number of protons and neutrons, or the presence of excess energy that the atom needs to shed. To achieve stability, these atoms release this excess energy in the form of radiation. This release can occur spontaneously or be induced by external factors, leading to the emission of particles or electromagnetic waves. This process is known as radioactive decay. During radioactive decay, an unstable atom transforms into a more stable form, often changing into a different element altogether. Radioactive decay can occur in different ways, each emitting a specific type of radiation with unique properties and energy levels. These types of radiation vary in their ability to penetrate materials and their potential effects on living organisms. The most common types include alpha particles, beta particles, and gamma rays. Each of these has distinct characteristics and interacts with matter in different ways. Alpha particles. These particles, consisting of 2 protons and 2 neutrons, are relatively large and heavy. Due to their size, they have a low penetrating power. They have low penetrating power and can be stopped by a sheet of paper or human skin. Despite their limited penetration, alpha particles can cause significant damage if ingested or inhaled. Beta particles. These high-energy electrons are smaller and lighter than alpha particles, giving them greater penetrating power. They can travel further in materials and pose a different set of risks and benefits. A thin sheet of aluminum can block beta particles. This makes materials like aluminum effective shields against beta radiation, protecting sensitive equipment and living tissues. Gamma rays. Unlike alpha and beta particles, gamma rays are not particles but rather high-energy electromagnetic radiation. They are similar to X-rays but with even higher energy levels. They possess significant penetrating power and require dense materials like lead or concrete for effective shielding. Gamma rays can penetrate most materials, making them both useful in medical imaging and challenging to contain. Understanding these different types of radiation, their properties, and their ability to interact with matter is key to comprehending both the benefits and risks associated with this powerful force. From medical treatments to energy production, radiation plays a vital role in modern science and technology, making its study essential for continued innovation and safety. Radiation as a healer, medical marvels. While radiation often evokes images of danger and destruction, it also plays a vital role in modern medicine, offering a range of diagnostic and therapeutic tools that have revolutionized healthcare. From simple X-rays to complex cancer treatments, radiation has become an indispensable ally in the fight against disease. One of the most well-known medical applications of radiation is X-ray imaging. By directing X-rays, a type of electromagnetic radiation, through the body and onto a photographic plate, doctors can visualize internal structures, such as bones and organs, allowing them to diagnose fractures, infections, and other conditions. Radiation therapy, also known as radiotherapy, harnesses the power of ionizing radiation to treat cancer. By targeting tumors with high-energy rays, doctors can damage or destroy cancerous cells while minimizing harm to surrounding healthy tissue. Beyond these widely used applications, radiation plays a crucial role in medical research, sterilization of medical equipment, and the development of new diagnostic and therapeutic techniques. As our understanding of radiation's biological effects continues to grow, so too will its potential to improve human health and well-being. Section 4. The power of the atom, energy production and beyond. This section delves into the profound impact of nuclear energy on our world, exploring its potential and the challenges it presents. The discovery of nuclear fission, the process of splitting atoms to release energy, ushered in a new era in human history. This groundbreaking discovery was a pivotal moment, marking the dawn of a new age of scientific and technological advancement. For the first time, we had harnessed the immense power locked within the atom, opening up possibilities for both progress and peril. The energy released from splitting an atom is millions of times greater than that obtained from chemical reactions, such as burning fossil fuels. Nuclear power plants fueled by uranium utilize controlled fission reactions to generate electricity. These plants operate by using the heat produced from fission to create steam, which then drives turbines to produce electricity. These plants offer a carbon-free alternative to fossil fuels, providing a significant portion of the world's energy needs. By reducing our reliance on coal, oil, and natural gas, nuclear energy helps mitigate the effects of climate change and air pollution. Beyond electricity generation, nuclear technology finds applications in various fields, including industry, agriculture, and archaeology. Its versatility extends far beyond power production, influencing numerous aspects of modern life. In industry, radioactive isotopes are used in industrial processes for gauging thickness, detecting leaks, and tracing material flow. These applications enhance efficiency, safety, and quality control in manufacturing and construction. In agriculture, radiation can be used to sterilize food products, control insect populations, and develop new plant varieties. This technology helps improve food safety, increase crop yields, and create more resilient plant species. And in archaeology and art, radiocarbon dating, a technique that relies on the decay of radioactive carbon-14, allows scientists to determine the age of ancient artifacts and fossils. This method has revolutionized our understanding of historical timelines and cultural evolution. While the benefits of nuclear technology are undeniable, its use also carries significant risks, highlighting the need for stringent safety protocols, responsible waste management, and ongoing research to minimize potential hazards. Ensuring the safe disposal of nuclear waste and protecting against radiation exposure are critical challenges that must be addressed to harness the full potential of nuclear energy responsibly. Section 5. The shadow of radiation. Understanding the risks. The same properties that make radiation so beneficial also make it potentially harmful. Ionizing radiation, with its ability to alter atoms and molecules, can damage living cells and disrupt biological processes, leading to a range of health effects. The severity of radiation exposure depends on several factors, including the type and amount of radiation absorbed, the duration of exposure, and the individual's age and overall health. High doses of radiation received over a short period can cause acute radiation sickness, characterized by symptoms such as nausea, vomiting, hair loss, and even death. Long-term exposure to lower levels of radiation can increase the risk of developing cancer, cataracts, and other health problems. Children are particularly vulnerable to radiation's effects, as their cells divide more rapidly, making them more susceptible to DNA damage. Understanding the risks associated with radiation exposure is crucial for establishing safety protocols, protecting workers in radiation-related industries, and responding effectively to accidents or emergencies involving radioactive materials.